I'll just wave hands if I need to get to the next slide if it doesn't work. So let's see how it goes. So so for people that don't know me, my name is Ilko Sjauron, and this talk is about running Open vSwitch on a system with a large number of CPUs. Can we get the next slide, please? Or I should try. I'm not sure if it worked. Is it me doing it? Oh, great. So it finally works. All right. So what was the objective for my testing was not to see how Open vSwitch will react under excessive load. It was just the idea of what happens if you have a system with a lot of CPUs instead of a number of cores under normal conditions. So nothing extreme, just replacing a 64 CPU system with 128 or even more, and see what the impact is on OVS. So I decided to first focus on some basic areas in OVS, which was the revalidator process, which gets a number of threads get increased when you have multiple CPUs in the system by default. I looked a little bit at the interface statistics. There's not much we can do about it, but it's the way the kernel handles per CPU type of statistics. So if you have multiple CPUs, there's more statistics. And then I also did some simulation of pod creation in a Kubernetes system, just to see, the impact if you have more CPUs in your system. What will it do to the time it takes to actually bring up those additional pods? And then, as a side note, when I was doing the pod creation simulation, I figured out that the get interface address function is also getting statistics, which might then relate back to the first, the second item here on the list. So what I used for hardware, I had a very basic AMD Dell system with, unfortunately, not very much memory. So there was not much I could run real Kubernetes on, but I could simulate. I was using RHEL 9 as the base with Open vSwitch 3.3. And then when I do the test, I either run in 128 CPU mode on that system or 64-bit CPU by disabling some of the cores in the system through the BIOS. So the first couple of tests that I did was the revalidation process. And just in short, I don't want to go over the details, but the revalidation process inside OVS is basically responsible to make sure that the datapad flows that are installed into the system sort of still match the OpenFlow rules that people have configured on the system. It also updates the byte and statistics counters for those specific rules based on the datapad rules that exist. And if a datapad rule is no longer used, it sort of flushes them out of the cache, and then the whole process repeats with upcall handling. I wrote a blog about it a while back, so the link is there if you finally get the presentation. But if you search for that thing, you will find it. So why is it different with a lot of CPUs? So if you don't configure the number of revalidator threads, by default, what happens in the system, it will figure out how many CPUs are available to the vSwitch D daemon. And then basically divides that by 4, adds 1, and that's the number of threads that you get. So on a 128 CPU system, that means you get 33 revalidator threads. So when I'm doing some comparison, I decided to have a very low number of threads, which is 4, either 32, which is not really 33, but I like the power of 2 numbers, and then also with the maximum number of cores in the system, and just compare the data. So how did I test this? So it's a very simple setup. I just create vEth interfaces. I put one of them in its own namespace, and then one through OVS. I have a very simple Scapy script that just sends traffic as fast as it can to fill up at least the 200K datapad entries that is enabled by default. And then I just see what the impact is on the revalidation process. One small thing to note here is I bind the Scapy to a single core, and I also do it with multiple cores because I run into a problem. So with this accidentally, so it would be good to see why later on. These are just configuration. I put them here for completeness so that if you want to replicate, you can do it. So what test did I run? So I run the test with 4, 32, or 128 number of revalidator threads, and I run 3 different tests. One is just generating 200K datapad flows with the traffic coming from one CPU, and I'll explain later why that is significant. Then I do the same thing with the 200K datapad flows, but I make sure that we need to revalidate all the 200K flows by 10 times a second, asking for a revalidation by changing some of the OpenFlow rules. So the system actually goes through the process of revalidating rather than only gathering the statistics. And then I do the same test as the first one, but this time I have the traffic sent from all the cores. And when we talk about it, I explain why. To measure stuff, I use the existing revalidator monitor script that's available in the repository with the existing USDT probe, so no changes to the code for this test, and get the data. Sorry. So for the 200K datapad flows with traffic arriving from a single CPU, here you see some of the results, and I think the only really interesting part here is the sort of average time it takes. So it takes about 170 milliseconds to process all the 200K flows when having 4 revalidator threads. Doing this for 32 threads, you see the time actually increases rather than decreases. So that's an interesting point here. Well, it's like 180 milliseconds. If I increase to 128, it's getting 3 milliseconds added to the total number on average. So what does that mean? So if you look at this in one type, you see it's like starting with 196, 181, going to 183. So it's basically increasing the time it takes to revalidate. Then I use some additional scripts that I've written and that are also available. At least the kernel delay scripts is available on the repository. And then the analyze perf PMD script is something I wrote a while ago, and I think I've used it before. It's a very simple perf script that it takes all the system calls that OVS vSwitch takes. It figures out what the callback trace is for that specific thing, and then records all those specific callback traces, group them together, and gives you the average time it takes to run that specific trace of callbacks through the system call. So when I was doing that, I found out that all that extra time is spent on a lock. So in this case, we are actually having a problem with some lock contention if we have multiple threads. And it comes bound to this function, and it has a little bit of explanation here why it actually takes the lock due to some Linux constraint. I haven't looked at it further than this. It's just an analysis part. So I think it will be good as a follow-up, just trying to figure out what to do with this and maybe try to fix it, then get rid of that lock to make it faster. So I did the same task, but with the revalidation sweep. So basically, that means that the revalidators have to spend more time trying to process all the flows. For this, I didn't put all the different slides there, but it's sort of shows the same thing. The only difference is here is that when you only have 4 threads, you see it takes longer because the threads basically need to process more data and verify the OpenFlow rules. But you see, if it's a 32, it's getting faster. But once again, if you have 128, it's getting higher again because the side effect of doing the sweep is no longer there. So I did the same analysis. So here in the same case, it's the dump lock contention. So it's basically the same problem if you have multiple threads here. And then the final test in this series is having traffic from multiple CPUs. And this was really interesting because when I started this test, I couldn't even run the test because my out-of-memory killer would kick in. So that was interesting. And after some analysis, I found out that it was due to a massive amount of flow stat allocations happening in my system. And just for understanding, this statistic or this data structure was allocated by the OVS kernel module. And what it does, when you have statistics for your specific datapad flow, for optimizations, we would like to keep the stats per CPU. But we only do that once we create the flow. We will create one CPU statistic set for that specific CPU that is processing the received traffic, which is fine. But then if the traffic comes from a different CPU, we will allocate another structure for that specific CPU, and then moving forward. So when I was running this with Scapy, unbound on the interface, it would just take whatever CPU was available to transmit that packet. So it will be, over time, it will basically allocate one structure for every virtual CPU, for every CPU in my system. So it was slowly, decreasing memory up to a point where you had like roughly theoretically 200K of them, and we would allocate about 780 megabytes of memory. And then if you would have a double system, it will 1.5 gigabit. So would that really be a problem? Probably not a memory problem. It was in my scenario because I allocated too much 1 gig high pages, which only left me with 1 gig of memory in the system, which I really didn't notice because I'm used to having a system with 128 gigs, so I didn't really care. So on my side, this was a misconfiguration, but it at least brought this to my attention on it. So what is really the problem, even though when I was continuing this, is that the main problem is the time spent actually accumulating all the statistics over the different CPUs, and mainly because it was in nonlinear memory. So we would be reading 128 times that data structure on different cache boundaries, and we would be trashing the cache quite heavily, up to the point where we actually spend more than 1.3 seconds in the revalidating process, which means we will drop down the maximum number of flows, and then we go to this visual cycle of having 200K databyte flows, dropping them all off, or at least dropping a good bunch off, so the revalidator process comes down, and it's sort of bouncing back and forth. This is not really something new, but because it already exists with 46 CPUs, but it's a different timing. It happens earlier with more CPUs. I didn't really go to the details, but the slides on the next, the graphs on the next slide might show a little bit on the effect of this. It might be hard to read, but at least you get the trend of it. So I'll quickly explain what the graph is about. This is with the tool that I mentioned earlier, so you can run it in your own system and get the same graphs or the raw data, whatever you want. So the first one is basically the slide is the number of flows that are currently in the system. So here you see we have about 200K of flows in the system, and it stays the same. The other line is not really important. It's the number of flows we revalidated over time. Here you see the slightly increasing dump duration. So here you see that we start with this 200K flows roughly around, takes about 400 milliseconds. And then once we add slowly over time, we add the additional statistic structures. We grow all the way up to about 380 maybe seconds. After 380 seconds, we hit that 1.3 second mark, and we drop the number of flows. And then revalidation takes less time, and it slowly builds up again until it gets there. So it's a repeating cycle, and it will never stop. This one shows the flow limit. So here we will drop the flow limit, and you also see that the average number of flows drop, and the maximum flow will stay the same because it's just the statistics that are normally from the revalidator process that we show here. And here it tells you how long we were actually waiting before we did another revalidation process. So by default, OVS will do a revalidation process every 500 milliseconds. But if the time it takes to run is longer than the 500 milliseconds, we will do an immediately recycle of that thing. That's what you see here. So once we drop down, we have a little bit of time to wait before we have to do the revalidation. But here you can see we start roughly around 400 milliseconds for the revalidation side. And then after 1.3 seconds, we drop down and we do it again. So which is about 300 milliseconds. This is with 4 revalidation threads. So there we go. So this is the same graph for 32 revalidation threads. It's roughly the same thing. The only thing to notice is we start very high and haven't really figured out why. So it already takes like 700, 800, 900 milliseconds. So when we increase, it takes a little bit faster before we drop off. So it's about 110 seconds, so like roughly 2 minutes before we drop the data path rules, and we slowly increase them again. So something to notice. And then the odd thing is with 228 revalidator threads, it's a little bit faster. It's faster in revalidating, and it also takes a little bit longer. So it's not really more threads is worse. It's like 32 seems to be the worst case scenario. But we haven't figured out what is the case. So I think this is something that needs some further research and see if we can maybe optimize the way we use the flow statistics. I guess in a real life scenario, it might not happen that much because NICs normally, are bound to a specific receive queue, which might be bound to a specific CPU. So you might not see it, but maybe traffic coming in from the vETH interfaces from the pods might exhibit this behavior. And this is with the 1024 interfaces, so it might be different with in different scenarios. All right, so the next thing, took my time, is the kernel interface statistics. Why did I look at it? Because a lot of drivers have per CPU statistics Although the good thing is they're normally linear in memory, so if we need to accumulate them, it's reasonably fast. So not as a worst case if they're all scattered around memory. But I did really want to see the impact to these. For this, I used the VE driver in my scenario, which are there. I also noticed that there are some net device core statistics, exception statistics that also use per CPU drivers as per CPU statistics. And those are mainly for some exception cases. I added them here, which are the ones that you see in IP stats if you use the IP stats command. But I just want to see the impact of using those as well. Oh, that's too much. So how did I test this? I tried to do it very simple. So I created 1024 VE pairs. One side is in its own network namespace. Other side is attached to OVS. Added 2 additional USDT probes to measure how long it takes to gather the statistics. I modified the bridge loop PT example script by just changing the 2 new probes. And then I run this test for about 5 minutes on a 64-core system and a 128-core system. And then I also did 2 variations, one with exception stats being present so that the data structures are allocated on the NetDef, and one without. There's the extra USD probes. So what you can see here is that for the CPU system with 64 CPUs, it's roughly around 63 milliseconds to run the statistics on those 1024 interfaces. When I have 128 CPUs, you can see that it's roughly doubling, or roughly 40% of more time spent getting the statistics. The problem is that's not really something we control as OVS. It's something that the driver developers have decided to use, but it's something to be aware of in this scenario. So I don't really have a solution for this other than ask every driver not to use per CPU statistics, but then you run into other problems. But it's just something, if you see a lot of time spent on the main thread, this might be one of the issues. So I did the same thing with the exception counter. So I made sure there are some exception counters on all the 1024 interfaces. Well, I think only 900 something interfaces, but they had the exception counter, so we had to add those too. And then you can see it increases a little bit with or without the exception counters. So it's not that much. So I think we should be fine. The other thing was that on a 64-core system, it was slower, and I didn't really figure out why. I didn't spend time in figuring out why it was slower on a 64, because we're basically using it from a single core, so there's not much to be done. So yeah, I know. Simulated pod creation. So I think the other thing I tried to test is simulating pod creation. We didn't have enough memory to do a real OCP cluster, so I just simulated it. I had 128 pods or vSwitch ports, which should be sort of pods in the system. And then I created 10 additional pods, add 10, delete 10, and I did that constantly, which took about 1.3 seconds per run, which I think is sort of in line with what the Kubernetes cluster will do, which is roughly 6 pods per second or so, I was told. And then there was no traffic. This is just creating the pods and destroying them. I'm using the same kernel delay Python script to do this. So I just got the output of the script, and I could see that most of the time was spent on the send message call, with roughly 50% more time spent on those calls on the 128 core system. When I did the analysis, I came to the conclusion that this is the actual callback. So it's basically in the netdef get addresses function that we spend most of the time, or the additional time. You can see it's like 58 sort of microseconds versus the 200 microseconds. So it's quite a bit longer on call on average. So I didn't really investigate why it's 2 times longer. I think that's still on my to-do list. I thought initially it's the get interface address function because it's getting the additional statistics. But I did some tests, and that's why I added the other one. It doesn't seem likely because that's only 6% overhead and doesn't really account for the 50% I see. So there might be some other RTNL or some other locking in the kernel happening when we are trying to get a lot of this interface statistics. Yeah, so I think this needs further investigation. So this comes back to the last test that I did, which is basically seeing if the get interface statistics is having a lot of overhead or not. So why I was looking at this, so basically this function gets all the IP addresses from all the systems, from all the NICs or all the interfaces in the system. But it's also getting the statistics for all those interfaces, and it's not reporting any of them back. So the reason is, why are we doing this? I don't know. But there actually is an option, from a kernel perspective into the API to not do this. So it might be, we're trying to rebuild, OVS, sorry, glibc with that option to see if it actually makes any change. But I guess my thing for this was just to sort of do the test and see, what the impact is on that function in general. So what I did is the same environment, the 1024 V interfaces, and then added 2 USDT probes around the get interface address function just to see how long that function takes. And I did that by running it for 5 minutes and doing 10 revalidations per second, because else we are not actually querying the interface address function. And that rather than giving everything, I just give you the summary. So it's about a 6% delta between the two. So it's still 6%, but it's not accounting for the 50% or even the 2.5 time in some of the times it takes to get that function. So yeah, so a quick test, and I haven't done it, is maybe patch the get interface address function and see if that 6% disappears or maybe becomes better somehow. So I think that's something that definitely can use some help. So what's the conclusion follow up of this? Some of the basic tests I've done. I think we need to explore if we can remove the mutex lock in the dump next function, or figure out a way that works for all the kernel versions. Then additional, we might want to take a look and see if that flow statistic structure that we allocate on use, we can maybe optimize that a little bit, use a different algorithm just to not allocate, the 1.5 gig by default, but at least maybe try to, find a middle ground where we might maybe allocate a couple or whatever. Then also, I think it's good to further analyze that the netdev get address function that we saw that takes a lot of time during the pod simulation part. See if we can get that sort of fixed. And then we could also probably try that quick glibc patch and see if that at least get rid of the 6% delta that we saw. And then of course, finally, this was very basic testing, just beginning, just replace the system and see what happens. But I think what I sort of left out was any upcall related testing. Is there anything, when we handle upcalls, there's more upcall handler threats, so there might also be more problems in that area. And then particularly around connection tracking and NAT maybe. But yeah, that's stuff to figure out. I think that's all I had. So I think if people have any questions, I think we can take them now. Also, if you feel like you want to work on any of those things, get in touch and we can maybe divide the work, or someone else can help out. That's it. So yeah, any questions? Oh, you're gonna drop the mic, I guess. Oh, not drop it, but bring it.
So what would you predict the resources are and the impact would be at like 768 or 1,000 CPUs? Because these are 64 CPUs is kind of I'm interested. I didn't really have any system higher than 128 at the moment, but yeah. So from a memory consumption, I guess if you look at the flow statistic, that would just increase linearly. So if you double the CPUs, you get more memory. Wow. But that might not be a problem. But like the lock on tension might be very interesting to see what happens in that scenario if you have a lot of CPUs. So from the revalidator thread perspective, it's configurable. So if you think that even on a 1024 system, if you feel like 32 revalidator threads is more than enough, you can just manually pin them down. The more interesting part, I feel like, is the kernel side. What if they have a lot of interfaces and they all do per CPU statistics, they might really gradually include that stuff. So I'm not sure if anyone in the kernel space is looking at that area. And are those processes bound to topology, or are they just Yeah, so what OVS does, it figures out what CPUs it's allowed to run on, and then based on that, it decides how many threads it's gonna allocate. But there is nothing that the revalidated thread is not really NUMA aware, so it doesn't really know that this specific NIC or those specific flows are handled by that specific NIC. So I'm gonna
Actually, that was my next question. In a NUMA system, and if if the NIC, the NetDev device or something, is on the second node, does it account for that? Will it match the CPU and memory correctly?
No, I think we're not doing any NUMA memory allocation inside of OVS.
Okay.
What about the CPU utilization? So at least in our data centers, we have seen that with 14,000 data path flow, the CPU is already 200, 300% doing revalidation. So in your case with 200K flows, what was the CPU utilization of the OVS?
Did I have? I'm trying to see. I don't think I had any slides with CPU. No, I don't think I put any slides with the CPU utilization there. And so sorry, I don't know the numbers from the top of my head. I can probably look it up for you. But I don't think it was extreme high in my scenario. Trying to remember top of my head. No, I'm going to make up numbers. I know, but it wasn't anything excessive. I think when it gets excessive is when you have a lot of up calls handling, which are that could become a sort of a spike. But the revalidation process, in theory, is not really high.
We do have one question from virtual, from Josh Messenger, and he asks, can we assume that more hosts involved in OVN overlay network can increase the revalidator process, or is the revalidator delay revalidator delay host specific and only relevant for interfaces on the local host?
Yeah, so it's only for the. I don't have to repeat the question, right? Because you have it in the mic. So it's only the flows that are actually installed that it's reading. So basically, if you have your datapath flows that are queried, those are only affected. So not the number of hosts that you have. For the revalidator process, I think the other one, the statistics are on the main thread, so they are involved with the number of interfaces that you have.
Okay, thanks. Let's thank our speaker.